Baseball is a bat and ball sport played between two teams, each consisting of nine players. It is widely regarded as one of America's favorite pastimes and has gained popularity worldwide. Thus, we introduce our project, Batterbot, a case study in trajectory optimization for non-prehensile manipulation. You might be wondering, why did we choose baseball for our project? First and foremost, it's a classic and one of our favorite sports, but it also provides very interesting manipulation tasks, such as elements of pitching and batting. Right now, there's limited literature on non-prehensile manipulation for dynamic aerial objects, where we define non-prehensile as when an object is not in the grasp for the entirety of a task, and this includes for pitching and batting, as the ball is not in the grasp of the pitcher or the batter for the entire duration of said task.
We start by setting up a simulation with Drake and DeepNote. Our simulation has two KUKA Iwa robot arms, each equipped with a shunked WSG 2-finger gripper. We also have models of a baseball and a baseball bat.
Our system simulates a simplified game of baseball in which one robot arm pitches the ball and another robot arm bats the ball. To pick up the baseball, the pitcher bot uses an antipolar grasp to maximize the contact area between the ball and the gripper, which allows for a very secure hold. To pitch the baseball, the pitcher robot chooses a randomly designed position within our design strike zone and calculates and executes a trajectory that can be generated. To bat the ball, the batter robot uses knowledge of the initial position and velocity of the ball and determines the trajectory to meet the ball at a desired position with desired velocity.
So we split the pitching motion into two pieces. One is picking up the ball from the floor, and the other one is throwing. So on the left, we have an example of picking up the ball. We execute this by defining 5 keyframes for the gripper to be in order to pick up the ball. And then we use inverse kinematics to solve for the joint angles at each of those keyframes. Finally, we linearly interpolate between the joint angles to define a complete trajectory. On the right, we have an example of throwing the ball. So throwing is slightly different because not only do we have a desired final position for the ball to be in, but we also have a desired velocity that we want to release the ball at. And so we initially attempted to use the exact same methods for picking to do the throwing. However, we found that trajectories that were generated using inverse kinematics were often jerky and caused the ball to slip out of the grasp of the robot. And so we switched to a kinematic trajectory optimization method that we'll talk about in a second. So here's the example of the other side of this, which is hitting the ball. So this is what is known as a bunt in baseball terms, which is hitting the ball at very low velocity. So the method that we use to compute the trajectory for the robot to swing the bat is in fact the exact same kinematic trajectory optimization that we use for throwing the ball. And that serves to show that this optimization method is somewhat generalizable and has good promise for tasks aside from simply pitching and hitting. So here are some more details about the trajectory optimization. So the swing of our robot is constrained by both an initial position, a final position, and a final velocity that we want the ball to be released at. So we generate the trajectory optimization problem by encoding these constraints within the pose of the gripper. And we tried 2 different methods. One was simply with position constraints, and the other one was with position and velocity constraints. And then to solve this optimization problem, we first solve an inverse kinematics problem for the robot joint angles at the initial position and the final position, and then use those as initial guesses to our solver to solve for the entire trajectory. And here are some key results that we observed. So we measured the error of throwing and of batting, throwing from 1 meter all the way up to 8 meters, and batting at different velocities from 0.5 meters per second all the way up to 4 meters per second. And these are some initial results that we had last night. And as of this morning, after some improvements, our hit and strike rate is now up to 100% at 4 meters away.
Now let's talk about some limitations of our design. Our design assumes that the Batterbot is aware of the pitch trajectory. In the real world, such information is not available. It will have to be estimated by the robot, which we can do using a perception algorithm. Also, our design does not apply air resistance or the hydroelastic contact modeling provided by Drake, and this will make the physics of the simulation more realistic. Looking forward to future work, we want to include visual pose estimation, which you can use by implementing an RGBD camera to generate a 3-point cloud. We can also model the gripper friction and release dynamics more accurately, which will improve the accuracy of our system. And finally, we also want to test the trajectory optimization framework for other tasks, such as pushing a chair or rolling a ball.
Thank you.